Hello, everyone. Welcome to Math Stats Coronavirus Edition. I hope that you're all doing well wherever you are right now. For the next 2 weeks, and hopefully that's all there is, I'll be recording lectures, and that way you can pause them, write your notes, think about them. I figured it would be better to use this format than to actually meet at a specific time and then try to have you all Skype in and work in real time. I figured this would be more convenient for all of us. And if you have questions, email me or post your questions in the forum. Couple reminders, your homework 4 is due on Friday. This should cover material that we learned before spring break. And you'll want to upload a copy of today's notes to Moodle. That includes both the notes we take now and a little activity I have you to do so that you can learn how to do these t-tests on RStudio. So there's some instructions for uploading it on Moodle. All right, so let's get started. So today we're talking about hypothesis tests for equality of two means. So what that means for us is we're going to have two populations, X and Y. X is going to be a normal distribution with mean mu X and variance sigma X squared. That's this piece right here. And Y is going to have a different normal distribution with a different mean and a different variance. So for today, we're actually going to assume that the two variances are the same. So we're going to assume that sigma x squared equals sigma y squared. This is just going to make our calculations a lot easier. So when you're doing a hypothesis test, you want to know, are the two means the same? Maybe you're comparing something between men and women. Do men and women both spend the same amount of time on Twitter on average, at least? Do they spend the same amount of time at the gym? Do they spend the same amount of time studying? You want to know this, and you want to take whatever you get from your data and run a statistical test to see how likely is it that my hypothesis is incorrect or correct. All right, so you're going to have different alternate hypotheses. Maybe mu x is bigger than mu y. Maybe women spend more time on Twitter than men. Maybe mu x is less than mu y. Maybe women at least spend less time on Twitter than men, at least. Or maybe they're not equal. The last hypothesis is what we do when we don't have an indication one way or the other that one is true or the other. So if you don't have any initial guess, you use the alternate hypothesis that their means are not equal. All right. So to do a hypothesis test, we have our options here on the left for the null hypothesis, that is H0, and the alternate hypothesis, which is H1. And what we need you to do is figure out what is the critical region. Remember, the critical region discusses what would lead you to reject the null hypothesis in favor of the alternate hypothesis. So what I want you to do is pause the video and go back to the other hypothesis tests we've done and go back to our confidence intervals when we did a confidence interval for difference of two means, and spend about 5 minutes and see if you can figure out what these critical regions are going to be. And then you can unpause the video in just 5 minutes or so and see if you were right. So I'm going to do 2 of them in just a few minutes, and then you can look up the other one if you really want to. But it's an important skill to be able to look at the formulas for the confidence intervals and then understand what the formula should be for the hypothesis test, because they're very similar. All right, now that you've had the opportunity to do that, let's find the critical region. So all right, sorry for that interruption. Let's see, where was I? Okay, so we need to figure out what the critical region is. So what we need to do is we need to define the t-statistic involved. And if you remember from last time, we can define it as follows. So the t-statistic for our difference of two means is the difference of the sample means divided by SP times the square root of 1 over n plus 1 over m. N and m, these are the sample sizes. And SP has this lovely formula. It is the square root of n minus 1 times sx squared plus m minus 1 times sy squared all over n plus m minus 2. All right, so using this information, we can define the critical region. So the critical region should look like T is bigger than or equal to T alpha of n plus m minus 2. So that is the region in which you would reject the null hypothesis. Now, if you want to know what that looks like in terms of actual test values, it is x bar minus y bar should be bigger than or equal to T alpha of n plus m minus 2. Let me see, let's move this over. Times SP times the square root of 1 over n plus 1 over m. All right, so that is the critical region for the alternate hypothesis that the mean of x is bigger than the mean of y. And I'll let you do the one below it. That's the case where the alternate hypothesis is that the mean of x is below the mean of y. And I'll do the bottom one. I'll at least show the t-value part. Here we want the absolute value of t to be bigger than or equal to T alpha over 2 with n plus m minus 2 degrees of freedom. And I'll let you do the rest of it. So these are our critical regions. And this helps us take our test statistic, whatever that is that we calculate, and ask, does it fall in the critical region? If it does, we reject the null hypothesis in favor of the alternate hypothesis. If the test statistic does not fall in that range, then we do not reject the null hypothesis. All right, so we're going to do an example, and we're going to use RStudio. First, we'll do it by hand, and then we will, I'll show you how to use RStudio to do all of this for you. Okay, so we're going to look at an example, and we're going to investigate bell peppers. Okay, example. So there's a certain pathogen that causes bell peppers to wilt and die. We think that too much water aids in the spread of the pathogen. Too much water aids in the spread of the pathogen. All right, so what we're going to do is they're going to take two fields and compare the soil water content in the two fields. So look at two fields. And compare the mean or average soil water content in the two fields. All right, and the units are percentage of water by volume of soil. All right, so I've entered this data into RStudio already, so we can go to RStudio and take a look at what is there. So we have these two fields, and I'm going to scribble out a piece of this that we don't need. You can ignore that piece right there. All right. And what we need to do is we need to run this t-test. See, we've computed the mean of A and the mean of B. You see we have our two fields here. Field A is the first vector I've encoded, and field B is the second vector. N and M are the sample sizes, and then I have their sample means and standard deviations and the degrees of freedom. So what we need to do is we need to figure out, first of all, what is the critical region? So we need to figure out, well, what's the quantile of T? And we're going to test this at the 5% significance level. So we want to do QT of 0.95, and we want n plus m minus 2 degrees of freedom. All right, so that's our critical region. If our t value is above 1.7, 0.1131, we'll reject the null hypothesis. If it's below that, we will accept, or we won't reject. All right. All right, so one thing we should investigate is whether we think it's reasonable that the two fields have the same standard deviation. This is important for using the method we just learned. So if I look at the standard deviation of field A, and I look at the standard deviation of field B, I see they're very similar. That's good evidence that supports our claim that the standard deviations are the same in the two fields. So because the sample standard deviations are so similar, we're going to proceed with using this t-test where we assume that the population standard deviations are the same. All right, now I need to calculate the t-statistic. So if you look back at what we had before, so let's take a look here, we can find that the t-statistic should look like, so I can find it. Should look like this. All right, so here's the t-statistic. We can do x bar minus y bar over sp times the square root of 1 over n plus 1 over m. So we need to calculate sp. So let's go to RStudio and calculate what sp is equal to. It's equal to the square root of, let's see, well, n minus 1 times sa squared plus m minus 1 times sb squared. And then we divide by n plus m minus 2. Okay, that should be sp. And we also need to then calculate the t-statistic. So the t-statistic, or the t-value, should equal the difference of our sample means, and we divide by sp times the square root of 1 over n plus 1 over m. And this should give us our t-value. Well, let's see what our t-value was. It was 2.005493. And so this is above our critical value. It's in the critical region. So we are going to reject our null hypothesis at the 5% level. So what does this tell us? It tells us that we reject the null hypothesis that field A has the same soil water content as field B in favor of the alternate hypothesis where field A has the higher soil water content than field B at the 5% confidence level. All right. So we still need to do a little bit of work though. We want to calculate the p-value. So to calculate the p-value, we need to find the probability that we got a t-value more extreme than this. So we want to do 1 minus the probability that we got a t-value that was more extreme than this with the correct number of degrees of freedom. And we get the p-value is 0.0273387. So this is our p-value. That's the probability that we would get a result that's more extreme than what we did, assuming that the null hypothesis is true, which we do not believe that it is. All right. So that's great. We've calculated the hypothesis test. We've calculated the p-value. Now let's actually look at a graph of the data to see what the depiction might look like. We're pretty confident that the mean of field A is bigger than the mean of field B. Well, let's visualize that data with a box plot. So we can look at field A, we can look at field B, and what we get the following side-by-side box plot, where this is field A, and this is field B, and we see pretty clearly that it looks like their medians are actually very similar, but pretty clearly field A has a larger mean than field B. And so all of this evidence is to convince you that field A has more water in it than field B. Okay, so we've done this by hand now. Wouldn't it be great if we could do this with RStudio, with our data, and not actually have to go through the rigmarole of doing this all by hand? Fortunately, there is, and it's called the t-test. So let's do the t-test. So the t-test, we have data A, we have field A, we have field B, but we've made some assumptions. The first thing we assumed was that the variances were equal. So we need the command var.equal is true. We also chose our alternative hypothesis to be greater than. That is, field A has a greater soil water concentration than field B. So if you do that, you will find that it gives us basically the same p-value with the same number of degrees of freedom. So this does it instantly for us and doesn't require us to calculate everything by hand. You see here that we've got our p-value. Let me circle it for you. Here's our p-value, and here's our degrees of freedom, and here's our critical value that we calculated this all earlier by hand. So that's one thing we can do. You could also do a two-sided hypothesis test. So when I just don't say anything, I don't include the alternative equals greater, it does a two-tail hypothesis test. And obviously, if I wrote alternative equals less, I think it's less, then it will give you the other one. All right, so these are the various alternative hypotheses. Now, I want to go back to the first one. Here we assume variance is equal as true. We can't always assume that. We could for this example, but when you cannot assume that the variances of the two populations are the same, you just don't include that command, and it uses a different routine to do a hypothesis test. You'll see actually that our p-value is very close to the one we calculated before, and that's because the two sample standard deviations were so close. That's how this p-value is so close to the one we did before. If the two standard deviations were pretty different, this p-value would not be as good. And yeah. So there's one more case that I want to mention. And in this case, you will sometimes see the case where we have paired t-test. So I can't use it on this data, but if you have paired data, you would use paired equals true. So we're not going to do this for this data set because it doesn't make any sense. But if, for example, you have data on, say, students at Lee with a workout program, and you compare how fast they run the mile before and after, that would be a paired t-test. You're kind of trying to see what was the net change of this program, this experiment, whatever. All right, so make sure that you've taken notes so far and work the things I told you to work. Last but not least, there is a file on Moodle under today's lecture that has 4 problems for you to work. You're going to use RStudio in all of these, and the data for these is already on Moodle under the March 19 data or data sets. And so I want you to write these examples in your notes and write not all the output from RStudio, but write enough of the output from RStudio so that I can see that you did that. I want you to be able to learn how to use RStudio in these cases, and I think you'll find yourself that when you get to writing your projects, you'll find this very useful. Let me know if you have any questions, post them in the forum, or email me if I'm not getting back to the forum fast enough, and I hope you all enjoy the rest of your week. Remember to get homework 4 in by Friday. Take care.